Hello everyone. I welcome you all in 7th lecture of Mechanics of Solids regarding Module 1 of this particular course, Stress and Strain. And up till now, we have discussed about two modulus. One was Young's modulus or modulus of elasticity, and the second was the shear modulus or modulus of rigidity. And in this lecture, we are going further with modulus called as bulk modulus, and with this diagram, say if the three mutually perpendicular stresses of equal intensity are applied to a body of initial volume V, and then the ratio of direct stress to the volumetric strain is called as bulk modulus. It is generally denoted by a capital K, and it is hydrostatic stress. It is also called as hydrostatic stress. So what exactly we are discussing about is, if three mutually perpendicular stresses of equal intensity are applied to a body of initial volume V, then the ratio of direct stress to the volumetric strain is called as bulk modulus. So sigma x, sigma y, sigma z all are equal to sigma. So all the three are equal, and then this ratio will be bulk modulus. It is mainly applicable to fluid problems with pressure intensity P in all the directions as shown in the figure. So something like this. If a body is there within the fluid and there is equal pressure from all the sides, then that may be getting compressed in this particular manner. So that kind of condition we are going to discuss about. So this is what already discussed, that bulk modulus is the ratio of direct stress to volumetric strain, and the stress everywhere is sigma, and divided by epsilon V, volumetric strain, is the bulk modulus. So epsilon V we have already written earlier, that sigma x plus sigma y plus sigma z 1 minus 2 mu divided by capital E. Now if all these sigma x, sigma y, sigma z together are sigma, then this sum becomes 3 sigma, and that will become 3. 1 minus 2 mu is written as it is, and this sigma is taken over here. So this K then becomes this minus sigma. So this as it is, and epsilon P is this total. Okay, 3, 1 minus 2 mu minus sigma divided by capital E. So if we rewrite this, what we get is this equation. This sigma and this sigma gets cancelled, and if this E, if we write it over here, and if we take this part 3 into 1 minus 2 mu on this side, then we will be getting equation E is equal to 3K multiplied by 1 minus 2 mu. So this K is called as bulk modulus. So what we have discussed is, if the three mutually perpendicular stresses of equal intensity are applied to a body of initial volume, say it is capital V, then the ratio of the direct stress sigma to the volumetric strain is called as bulk modulus. And then this equation is giving us what is the relation between Young's modulus and bulk modulus. So similarly, we can have one more equation regarding Young's modulus and shear modulus. And today what we are going to discuss further is what is the relation between all these three moduli, that is E, K and G. So we'll go further with this discussion, relation between elastic constants E, G, K and mu. So again we are going to this particular diagram. So we have shear stress tau acting on AD and BC, and on DC and AB we have tau dash, that is complementary shear stress. And due to this, now if this tau and this tau dash is acting on this diagonal AC, then that diagonal AC will be subjected to tension and diagonal BD will be subjected to compression. So that B dash D dash is the final position of that BD diagonal, and A to C dash is the final position of diagonal AC. And with this, if we draw it something like this in this way, okay, so instead of taking it on this side, it is drawn in this way. So what we can say is D D dash and B B dash is this position is as it is, B dash is at B, and this is the elongated position of AC from this position up to AC dash, like this. Okay. So if we go through this particular diagram, what we can write is something like this: linear strain of the diagonal AC. So for this diagonal AC, the linear strain will be what? Epsilon is equal to AC dash minus AC. So AC dash is final position and initial position is AC, initial length. So the change in length will be AC dash minus AC, and original length is AC. So change in length divided by original length is strain. And now what can be written is AC dash minus AC is equal to E C dash. So E C dash divided by AC. So if we go through this diagram, what can be written is this E C dash and C C dash, relation between this is cos of 45. So if this angle is 45, and if we are considering over here, this is very small. So if we consider this as 90 degree and this as 45, so what we can write is relation between this E C dash and C C dash, as E C dash divided by C C dash is cos of 45 over here. So what we can write further is this E C dash, we are writing it as, instead of E C dash, we are writing it C C dash cos of 45. So C C dash cos of 45. And for AC, what we are writing is, if this is AC, then cos of 45 is this AB divided by AC. So for AC, what we can write is AB divided by cos 45. So CC dash cos 45 stands for EC dash, and AB divided by cos 45 is written in place of AC. So that this can be written as, now what we are writing is, if we are considering this angle, now this was phi by 2 and this was phi by 2, and total together is phi, is the shear strain. Okay, so what we can write is tan of phi is equal to phi. So this term can be written as CC dash divided by BC. Over here, tan of phi at this position is this. If this is phi and if this is phi, then tan of phi is C dash divided by this part, BC. Okay, and AB is equal to BC. So over here, what can be written as, this is this CC dash. CC dash becomes BC into phi. BC into phi. And this cos 45, if we take it on this side, this will give us cos square 45. And AB and BC, if we write it same, so if instead of AB, if we write it as BC, this BC gets cancelled, and cos square 45 is half. So what remains is epsilon is equal to 5 by 2. So with this, what further we can write is modulus of rigidity. You are aware that it is capital G given by the ratio of shear stress to shear strain. So phi, again we are knowing that it is tau divided by G. So if we put it over here in this equation, epsilon is equal to 5 by 2. So phi is equal to tau divided by G. So epsilon is equal to tau divided by 2G. 2 is as it is, and for phi we can write it as tau divided by G. And now what is over here is, now this is in compression, this BD diagonal is in compression and AC diagonal is in tension. Then in the state of simple shear on two perpendicular planes at 45 degree are subjected to tensile stress on a diagonal plane and compressive stress on the other diagonal plane. So that is what is drawn over here. The magnitude of both these stresses each are equal to tau. So all the stresses are tau. So the magnitude of both these stresses, it may be tension or compression, will be equal to tau. So due to that, what will happen is epsilon is equal to, along this AC, that will be tau divided by E. If tau is say sigma on that particular length K, or along that longitudinal axis AC, if it is tau, on another diagonal BD if it is compressive, then with lateral strain and linear strain, what we can write is epsilon is equal to tau divided by E. So for this diagonal AC, this longitudinal strain will become tau divided by capital E. And due to what is acting on diagonal BD, due to that there will be again elongation along axis AC. So that is lateral. So what is written for that is minus mu times tau divided by capital E. And this minus, then it gets plus, and then both will be trying to elongate that diagonal AC. So this equation then becomes as tau divided by E. If it is taken out, then what is remaining is 1 plus mu. So this equation, epsilon is equal to tau divided by E, 1 plus mu. What we can write then is, earlier that was epsilon is equal to tau divided by 2g, and now over here we have equation epsilon is equal to tau divided by E, 1 plus mu. So now if we equate these together, so this tau gets cancelled and we can have some relation between E and G. So what will happen if we take E on this side and 2G on this side? E is equal to 2G 1 plus mu. So earlier we have this equation which was relation between E and K, and now we have equation 2 in which we have relation between E and G. Okay. So if we go through equation 1 and equation 2, E is equal to 3K 1 minus 2 mu, and with this what we can write is 1 minus 2 mu is equal to E divided by 3K. What is written further, and with this second equation what we have, E is equal to 2G 1 plus mu. So for if we multiply it by 2 inside, so it will become 2 plus 2 mu. Okay, and if we take this G on this side, that will become this capital E divided by G. So we have two different equations. 1 minus 2 mu is equal to E divided by 3K, and 2 plus 2 mu is equal to E divided by G. So if we use these two equations, if we add these two equations, what will happen is, now this 1 plus 2 becomes 3, these two gets cancelled, and this will give you E divided by 3K plus E divided by G. And if we go further with this, what we can get is this relation. So if we get this E outside, then over here it will give you 1 divided by 3K, and over here it will give you 1 divided by capital G. So what we can do is this 3kg, if we take it out, then over here this will become G plus 3K divided by 3kg, so that E and 3kg is taken out. So what is remaining is 3K plus G. So if we take this 3kg on this side, and this 3 and this 3, it becomes 9. So, and this will give you 9 kg, and if we take this 3K plus G on this side, it will be E is equal to 9 kg divided by 3K plus G. So this is the third equation, which is giving us a relationship between E, K and G. So what we have discussed up till now is these three equations. So first equation was a relationship between Young's modulus and bulk modulus. So that was E is equal to 3K 1 minus 2 mu. And the second equation was a relationship between Young's modulus and shear modulus or modulus of rigidity. So that equation was E is equal to 2G 1 plus mu. And then we discussed about third equation. That equation is a relationship between elastic constants E, G, K together. So that equation becomes E is equal to 9 kg divided by 3K plus G. So with this discussion, we will go through few numerical. Say this statement of the numerical 10 is like this. A steel bar of 20 mm diameter is subjected to axial tensile load of 45 kilonewton. If the change in diameter is found to be 0.003 millimeter, determine the Poisson's ratio, modulus of elasticity and bulk modulus. So Young's modulus is to be calculated, bulk modulus is to be calculated, and what is given is the shear modulus or modulus of rigidity, capital G, as 110 gigapascal GPa. So what is given is not change in length. So what is given is change in diameter and original diameter. Okay. So we'll discuss how to go for its solution. So what is given is area of cross section. We can calculate it with what is diameter was given. So that was pi by 4 d square, and the force to which it is applied is 45 kilonewton. So stress becomes sigma P divided by A. So that will be 45 converted into Newton into 10 to the power 3 divided by area of cross section, that is pi by 4 d square. So this calculation will give us stress as 143.24 Newton per mm square. So with this, what we can calculate is, now what is given is change in diameter, that is 0.003 millimeter. So with this change in diameter, what we can calculate is change in diameter divided by original diameter will give us lateral strain. So lateral strain, if we calculate it, it gives 0.003 divided by 20 as 1.5 into 10 to the power minus 4. So with these two calculations, what we have stress sigma. So this stress is longitudinal stress, and this strain is lateral strain. And relation between these two we have discussed earlier, that was lateral strain is equal to minus mu times the linear strain or longitudinal strain, and for that we can substitute it as sigma divided by capital E. So this relation becomes mu times sigma divided by capital E. So lateral strain now it is known to us, and this sigma is known to us. But these two terms which we are unknown or which are required to be obtained is Poisson's ratio and modulus of elasticity. So what we can do is capital E is equal to, we substitute this sigma over here 143.24, and then this lateral strain is substituted over here 1.5 into 10 to the power minus 4. So we'll be getting some equation in between capital E and mu. So that becomes E is equal to this complete term 954,933.33 times mu. So knowing this, what we can do further is, we are knowing the relationship between E and G. So this equation we have discussed earlier, that E is equal to 2G 1 plus mu. So out of this, G is now known to us, it is given. So what we can write is E is equal to 2 into this 110 is given. So 2 into 110, it is in gigapascal converted into megapascals or Newton per mm square by multiplying it by 10 to the power 3 and 1 plus mu. So if we substitute it inside, what we'll be getting is this term plus the same term multiplied by mu. Okay. So now with these two equations, equation 1 and equation 2, we have two unknowns, E and mu. So if we solve these two equations, what we can write is this term, and now this can be calculated, this Poisson's ratio can be calculated with this as mu is equal to 0.3. And once again you can substitute this mu as 0.3 either in equation 1 or in equation 2, and we can calculate what is Young's modulus. Okay, so substituting this mu in equation 1, we will be getting this Young's modulus as 285.87 into 10 to the power 3 Newton per mm square. So now we are knowing this E and mu, and now we can use what is the relation between E and K. So now this equation we have discussed earlier. E is equal to 3K 1 minus 2 mu. So if we substitute now what is Young's modulus and what is Poisson's ratio in this equation, what we will get is this K is taken on this side, K is kept on this side as it is, and E. So what we can write is E divided by 3, 1 minus 2 mu is over here. So what it will become, as this E is substituted as it is and mu is substituted over here, and we can calculate this bulk modulus as 238.22 into 10 to the power 3 Newton per mm square. So what is given in this numerical is regarding lateral strain. This change in diameter and original diameter is given. So with this you can find lateral strain. So in earlier numerical, what we have done was stress sigma was calculated and the longitudinal strain was calculated, and with this stress and strain we have calculated the Young's modulus. Okay, so here the change in length and original length is not given. So with change in diameter and original diameter we have calculated lateral strain, and with the other equations we try to calculate the Young's modulus and the Poisson's ratio. Okay, so with this numerical we will again go through one more numerical, that is numerical 11. The statement of the numerical is something like this. An axial load of 65 kilonewton is applied to a bar of 33 millimeter diameter and 1 meter length. The extension of the bar is measured to be 0.3 mm. So it is the change in length, whereas the reduction in diameter is 0.003 millimeter. Calculate the Poisson's ratio and values of 3 moduli. So all E, G and K is required to be calculated. So we'll go one by one the solution of it. Now change in length is given, delta L is given, and capital L, that is the initial length, is known. So with this we can calculate longitudinal strain. So epsilon is delta L by L. So this 0.3 is change in length divided by original length 1 meter. So it is in millimeter, 1000. It gives us 3 into 10 to the power minus 4. And similarly, what we can calculate is lateral strain. So lateral strain is in another dimension. So that is change in diameter to original diameter. So delta D is given 0.003 and original diameter is 30 mm. So if we calculate this, it will give us 1 into 10 to the power minus 4. So with this further, we can find what is Poisson's ratio. So this relation is known to us, that Poisson's ratio is the ratio of lateral strain to longitudinal strain. So this lateral strain is 1 and longitudinal strain is 3, and if we calculate it, we will get mu as 0.33. So that is Poisson's ratio. And with this, now if this stress is calculated, if this load is known and area of cross section is known, so load divided by area, so 65 kilonewton is the force applied at that particular position, and original diameter is 30 mm, so area of cross section becomes pi by 4, 30 square. So with this calculation we get stress as 91.956 Newton per mm square. Now when this is known, then this modulus of elasticity or Young's modulus then will be the ratio of the longitudinal stress to longitudinal strain. So this 91.956 is sigma, and epsilon, that is longitudinal strain, is 3 into 10 to the power minus 4. So if we calculate this, then we will get this modulus of elasticity as 306.52 into 10 to the power 3 Newton per millimeter square. So now we know the relation between E and K. So with this equation, what we can write is K is equal to E divided by 3, 1 minus 2 mu. So E is calculated now, and mu is also calculated. So if we substitute that, we can find what is bulk modulus, and that calculation will give you capital K as 300 into 10 to the power 3 Newton per millimeter square. And using this relation, another relation what we know is in between Young's modulus and the shear modulus. So with this we can calculate G as G is equal to E divided by 2 1 plus mu. So with this, if we calculate the shear modulus, value of shear modulus becomes 115.23 into 10 to the power 3 Newton per millimeter square. So with these two numerical 10 and numerical 11, I am concluding this lecture. I am thankful to you all. Thank you.